Good morning, good evening, good afternoon, people, and welcome back to another math lesson. Today we're going to be moving on to our radicals and rationals unit for grade 12 pre-calculus. So let's start off with lesson number 1, talking about properties of radical functions. So the function y is equal to the root of f of x is the square root of the function y equals f of x. Okay, so you're just square rooting the y values. The function y equals the root of f of x is only defined for when the original parent function, okay, so the original parent function f of x is greater than or equal to 0. Okay, so for your original function, that's basically when your y is greater than or equal to 0. Okay, so that's again for your parent function. That's for your original function. Okay, so that's the function that hasn't been square rooted yet. Okay, the domain of y equals the root of f of x consists only of all values in the domain for which f of x is greater than or equal to 0. So basically the domain only exists when, again, it circles back to when y is greater than or equal to 0. Okay, that's for when your domain exists. When y is greater than or equal to 0, that's where your domain will start. The range for y equals the root of f of x consists of the square roots of the values in the range of y equals f of x for which the root of f of x is defined. Circles back to y equals y is greater than or equal to 0. Okay, so that's what it's talking about. Okay, so the range of the root of f of x is only defined for when the original function you have for when y is greater than or equal to 0. Okay, this last one will highlight invariant points occur when f of x is equal to 0 and f of x is equal to 1. So again, that is when y is equal to 0 and y is equal to 1. Okay, that's for your original function because it's the same value, right? The square root of 0 is 0 and the square root of 1 is 1. So that's why those are your invariant points for radical functions. Okay, so let's start off with an example. Example number 1. It says sketch the graph of y equals x and y equals the root of x. Okay, well, you should already know how to graph y equals x. So let's go ahead and do that real quick. Okay, so you can see that this is our y equals x. Again, it's your regular linear line. Okay, so now what we are going to do is we are going to do y equals the square root of x. Okay, so in this, essentially all we are doing is we are going to take the square root. Okay, so when x is equal to -2, we take the square root of that. So it's like the root of -2, and the square root of any negative, okay, is undefined. Okay, so we're going to write that as undefined. Next, we have x is equal to -1. Well, it's the same thing. Any root of a negative is going to give you undefined. So it does not exist, okay? So we can't graph it, okay? The square root of 0 is 0, okay? Now, the square root of 1 over 4, okay, so that's 0.25. It actually equals 1/2. It's actually bigger, okay? So that'll actually come into play in a moment, okay? The square root of 1 is 1, and obviously you know the square root of 4 is 2. Okay, so let's go ahead and let's graph this. So again, we're going to start at 0, okay? Then the next one is 1/4 and a half, so that's about here, okay? And then the 1, okay? And then at 4, so 2, 3, 4, it's going to be 2, okay? So your graph is going to look something like this. It's going to come up above the original, touch the next point, and carry on. Okay, so that's what your root graph will look like when you sketch it out. Okay, so again, notice how in between 0 and 1 for x, your y values are actually going to be greater than the original function y equals x. Okay, so in between these two, your root graph is going to be bigger than your regular graph. So that's it. Just in between 0 and 1. Oh, in between 0 and 1/4, my mistake. Let's change that real quick. In between 0 and 1. Okay, so in between. Because 0 and 1, they're equivalent. But in between 0 and 1, your root of x will actually be bigger than x. Okay? Which brings us down to the characteristics of radical functions. So the characteristics of radical functions, again, the value of y equals f of x, okay, that's the title of the left column, and then the relative location of the graph is y equals the root of f of x. Okay, so your original function, so f of x is less than 0. The root of f of x is undefined. Okay, so and that's what we saw up here. So when we had the root of x is equal to -2, or sorry, when x is equal to -2, the root of x does not exist. Okay, so anything below 0 does not exist. When it's equal to 0, that's where they intersect. So that's where your original graph and your root graph, or your radical graph, will intersect, or they'll meet, they'll cross at that point. Okay, so this is also, and let's make a note of this, this is also our invariant point. Okay, so this is an invariant point. Now, in between 0 and 1, that's when your root graph will be higher than your original graph. Okay, so that's why you see a little bit of a bump. So let's make a little note of that. That's where you'll see the bump. Okay, when f of x is equal to 1, that's another invariant point. Okay, and then when your f of x graph is greater than 1, right, that's when your root graph will be below your parent function graph. Okay, so those are all characteristics of radical functions. Okay, example 2. Given f of x is equal to 3 minus 2x, sketch the graph of f of x is equal to the root of f of x. Okay, so we're going to sketch both the original graph, and then we'll sketch the root graph. Okay, so we will sketch both. Okay, we're going to sketch the first one. We're going to go y is equal to 3 minus 2x. Oop. Okay, for this one, let's find the x-intercept first. Okay, so that's when y is equal to 0. Okay, so 0 is equal to 3 minus 2x. Move the 3 over, so you get -3 is equal to -2x. Divide both by -2, and you should get x is equal to 3 over 2. So that's where your x-intercept will be for your parent function. So 3 over 2 is right there. Okay, to find your y-intercept, that's when you set x is equal to 0. So we have y is equal to 3 minus 2 times 0, which means that y is equal to 3. We can put that on our graph as well. We'll draw a line, okay, and that's our linear function there. Okay, now that we've finished the original function, let's draw out the root. Okay, so we're going to draw out the root graph now. Y equals the root of 3 minus 2x. Let's clean that up. 3 minus 2x. Okay, so in this one, again, we have our invariant points, right? So recall from the characteristics of radical graphs, the invariant point as y equals 0, that's start. Okay, so when y is equal to 0. So y is equal to 0 right here, where it crosses the x-axis. Okay, so the next part will be when y is equal to 1. And y is equal to 1 right there. So in between those parts, okay, you'll draw your bump. Okay, so you draw your bump so that it's just above. Okay. Next, what you will do is find any other perfect square numbers. 4, 9, 16, so on. Take the square root of those, okay? And that'll be where your next point will be, okay? So you can look along your y values and find when the next one is, okay? That will be your corresponding x, okay? So let's go ahead and try and find some values there. So this is 3, 4, so 4 will drop down to be 2, okay? And then 9 should be up here, so 9 will drop down to 3. So we can go ahead and continue our graph, like so. And there is our radical function. Okay, so that's how it is sketched. To state the domain of this radical function, we can state it so that the domain is all your x values such that x is going to be less than or equal to 3 over 2, provided that x is an element of all real numbers. Okay, so that's your domain. Your range, okay, is going to be all the values of y such that y is going to be greater than or equal to 0, provided that y is also an element of all real numbers. So this is one way you could write your domain and range. You could also use brackets as well. So you can go round bracket. Okay, so round bracket. So this is going to be negative infinity to net 3 over 2. I was going to say negative 3 over 2, but that's not right. And make sure this is a square bracket at the end. Okay, and then for the last one here, for range, it could be, again, negative infinity. Oh, no, sorry. It starts at 0, so we want square bracket. We want it starts at 0 and goes to infinity. So there you go. That's how you can write it in this other notation as well. Okay, so both are acceptable. Make sure you check with your teacher to see which one they prefer or if they have a preference. Okay, so make sure this is just an example of how you can write it both ways. Okay, moving forward, I'm going to write it in terms of, I'm going to write it this way, okay, for your domain and range. Which brings us now to the steps to graphing. Okay, so step number 1 is to locate your invariant points and plot them on the graph. So again, that's when y is equal to 0 and y is equal to 1. Okay, so those will be your invariant points. That's when you plot them. Okay, so that's step number 1. Step 2 is you draw part of the graph between the invariant points above the f of x. Okay, so that's where you would draw your bump. Okay, so that's where you would draw the little bump that goes above the original function. Next is you locate other key points at perfect squares and draw them below. So that's when you would draw, again, you would look for 4, 9, 16, 25, and keep going like that. Okay, and drop them down to their square root. And finally, you sketch a smooth curve between the points and remember the shape of a radical function. Okay, so note, let's highlight this. Nothing should be below the x-axis. Nothing. Okay, so everything below the x-axis, okay, does not exist. Okay, this does not include transformations. Okay, this only includes the properties of a radical function. So with transformations, you can pick up and move graphs wherever. Okay, but this for steps to graphing only applies to properties of radical functions. It does not apply to transformations of radical functions, and we'll go through some examples of that. Okay, example 3. Given the following graphs, f of x, sketch the graph of the root of f of x and state the domain and range of both. What we'll do is we'll state the domain and range of the radical function, as I'm sure you can figure out what the domain and range of these graphs are, the original graphs are, okay? So we're just gonna sketch the root of f of x and then state the domain of the radical function, okay? All right, so again, for your steps to graphing, you want to find the invariant points first. So find out where y is equal to 0 and y is equal to 1 on your parent graph. Okay, so when y equals 0, that's when it crosses the x-axis. So we can go ahead and we can plot our point right here. Okay, when y is equal to 1, again, you see where y is equal to 1, and that's where you plot your point there. The next point says to make sure you draw so that you have a bit of a bump, so that you can see the spacing in between. Okay, to show that that's greater than your original function. Okay, the next step is to find all other values, like all the other values of perfect squares, 4, 9, 16, and so on. Okay, so here's 4, so we'll drop it down to 2, and this is 9, so we'll drop it to 3. Okay, next is you were to sketch a smooth curve. Make sure you keep it in the shape of a radical function. When you get used to drawing out radical functions more and more and more, so when you do more questions, you'll be able to skip step 2, okay? Just find all your points and then you're able to plot them. The only thing is don't forget the bump. That's the only thing, okay? So we just did the invariant points. Y is equal to 0 and y is equal to 1. We did the bump. Okay. We found other perfect squares. Okay, and then we graphed. So that's 1, 2, 3, and 4. Last thing we're going to do is state the domain and range. So the domain, okay, is going to be x such that x is going to be greater than or equal to, I think that's negative, let's count. 1, 2, 3, 4. So it's going to be negative, everything's greater than negative 4, provided that x is an element of all real numbers. Okay. Next up is the range. So the range is going to be y such that, again, it's going to be everything is greater than or equal to 0, provided that y is an element of all real numbers. Okay. So there you go. There you have it. That's this example for graphing a radical function. All right. Next up, we have this graph. This is our new f of x. Okay, so it's an upside down parabola, so it's a parabola that's going in the negative direction. Okay, so what we're going to do again is just go through our steps of graphing radical functions. So we'll find our invariant points first. Okay, that's wherever y is equal to 0 and y is equal to 1. So in this case, there's going to be 4 invariant points because it crosses in multiple spots. So there we have y is equal to 0 and y is equal to 1. Okay, the next step is for you to graph the bump. Okay, so the bump's gonna look a little weird, but it looks like it's coming around back, but it's not. Okay, so it's just you just need to exaggerate a little bit to show that your radical function is going to be greater than the original function for your y values in between those 2 points. Okay, next up is you find your perfect squares, 4, 9, 16, and so on. Let's go ahead and let's find that for our y values. Okay, so our y values. So this is 2, 3, 4. So we're going to drop that down to 2. Okay, so this is 9, so we'll drop it down to 3. And since it's a parabola, it'll be mirrored. So it's going to be the same thing, but over here. Okay, the next thing is you will to draw a smooth curve to connect the points. And then you're done. So it looks like, again, I'll kind of redraw the points here. So it looks like a mini parabola within a parabola, but that is how you would sketch this particular graph. Again, hopefully your lines are a little bit more straighter than mine, but that's okay. That's why they're sketches. Okay. Next is the domain. So the domain for this one is x such that we're going to be in between 2 points. Okay, so it looks like we're in between for x is -1, 2, 3, 4, 5. So we're going to start at -5. It's going to be less than or equal to x, which is less than or equal to 1, provided that we want all x's to be real numbers. Okay, and then the range. Okay, so the range is going to be, looks like from 0 to 3. So it's going to be the same thing. Y such that it's going to be 0 is less than or equal to y, which is less than or equal to 3, provided that y is all real numbers. Okay, so that's how you would graph this example. Moving on to the next example, again, we're going to follow the same steps to graphing radical functions. So start with your invariant points. So when y equals 0 and y equals 1. Again, this is a parabola, okay? So you'll have 4 invariant points, okay? So the next bit is you are to draw your bump. So we're going to go ahead and draw our bump, okay? Now, the reason why our graph is trending in these directions, okay, is because of how our original graph is trending, okay? So because it's opening up and moving outwards, that's where our radical graph will move as well. Okay, so the next bit is find all the values. Okay, so your perfect square values. So 4, so this is 1, 2, 3, 4. So we'll drop that down to 2. And it's a parabola, so it's mirrored. Okay, and then we're gonna go to 9. Here's 9. And then we'll drop it down to 3, and it's mirrored. So it's going to be the exact same on the other side. Last thing is we're going to connect our points, making sure that it is a radical shape like so. There you go. So that's how this particular graph would look. Again, the domain is going to be split into 2 parts. Okay, so it's going to be x such that we have, what's this? 1, 2, 3. So x is going to be less than or equal to 3. And also, for this one, what's that? 3, 4, 5, 6, 7. So x is going to be also greater than or equal to 7, provided that we have x as an element of all real numbers. Okay, for a range, it's a lot simpler because we're only dealing with our y values, and it looks like it starts at 0 and then carries on. So y such that y is going to be greater than or equal to 0, provided that y is an element of all real numbers. Okay, so there you go. For this particular example, the domain can be a bit tricky, okay, but that's how you would write your domain and range for this particular example. Moving on to the next example, what we're going to do is, again, follow the same steps for graphing radical functions. So we'll start with our invariant points when y equals 0 and y equals 1. Okay, next off is you were to draw your bump. So it looks like it's going to go in 2 different directions. So there's the first direction and then the second direction. So we mirrored going in the opposite direction. Next up is you were to plot the points of perfect squares. So there's 4, there's 2, and it's mirrored. 3 and 3. Next up is you were to continue your points. Oops. Oops. There you go. Okay, so that's what the graph will look like. Again, writing the domain and range. So the domain looks like x is going to be all real numbers. It can be any x. There are no restrictions on x in this case. But for the y's, there will be. It's going to be every value of y such that y is going to be greater than or equal to 0, provided that y is an element of all real numbers. Okay, so there you go. That's this example. Okay, we can sketch radical functions using transformations if we were given an equation of a graph with a radical symbol. So now we're going to do radical graphs with transformations to them. Okay, so the first one is example 4. Example 4 says sketch the graph of y equals 2 multiplied by the root of x plus 3. So we're going to do this using mapping notation. So how that works is we're going to set up the original graph, y equals the root of x, and we're going to get specific points from there. So the specific points for a radical graph, so just the root of x, is 0, 0, 1, and 1, 4 and 2, 9 and 3. Okay, so again, what I would recommend is for you to understand and know that these are the points that you could use to help with your mapping notation throughout this unit, okay? Okay, so now the mapping notation goes alongside of with what we're doing to this graph. For transformation-wise, are we stretching it? Are we compressing it? Are we shifting it? Okay, so that's what we're doing, okay? So in this particular graph, okay, everything on the outside of the root, okay, is vertical stretch, compression, or shift. Okay, everything under the root is going to be a horizontal stretch, compression, or shift. Okay, so everything outside the root is you're going to do stuff to your graph vertically. Everything inside the root is you're going to do things horizontally to a graph. Okay, so in this particular case, it says x plus 3. Okay, so that's going to affect your x values. Okay, so you're actually going to subtract 3. So you're going to move this graph 3 units to the left. Okay, and then for the y's, you're actually going to double your y's. Okay, because the 2 is on the outside of the root, so that's going to affect your graph vertically. Okay, the 3 is on the inside of the root, so that's going to affect your graph horizontally. Okay, and it's usually the opposite of what it tells you. So for under the root, for example. Okay, so if this one says it's plus 3, so what we're going to do is we're going to subtract 3 from it, okay? If it said to multiply under the root, okay, then we would divide, okay? So we would divide the values, okay? So that's how that works. So what we're going to do is we're going to map out this new graph, okay, using this mapping notation, okay? So instead of the graph being at 0, 0 now, well, we'll subtract 3 from x, so that's now at negative 3, and we'll multiply the 0 by 2, well, that's still 0. So all we've done is we've moved it to the left 3. Okay, this next one, okay, we're going to subtract by 3, so we're going to get negative 2, okay, and then we're going to multiply the 2 by 1 for our y value, which gets the value of 2. Next up is we subtract it by 3, so we get 1, and then we go 2 times 2, which gives us 4. And the last one here, we have 9 minus 3, which is 6, okay, and then 2 times 3, which is also 6. So those are our new points. So we can go ahead and we can graph them. So it starts at negative 3 and 0. Okay, then negative 2 and 1. Then 1 and 4. Oh, sorry, negative 2 and 2, my mistake. Negative 2 and 2. 1 and 4, and then 6 and 6. So this is 6. 2, 3, 4, 5, 6. So those are our new points. And we can go ahead and sketch them. Like so. Okay, so that is how you would do, that's how you would graph this particular example using mapping notation. All right, part B is going to be looking at using the characteristics of radical functions. Okay, so that's kind of what we're going to be doing with our steps. Okay, so let's go ahead and let's kind of plot out some of the points here. So if we do number 1, let's do just the original y is equal to x plus 3. Just the original, okay? So the original linear function of y equals x plus 3, okay? It kind of looks like this. Okay, so that's what our original graph would look like. If we now were to put it under the root, so y is equal to the root of x plus 3, okay, well now we can use our characteristics. Okay, we can use the steps to graphing, where we would start at y is equal to 0. So here it is, at y is equal to 0. Okay, and then the other invariant point is when y is equal to 1. Okay, then we would find other points, okay, that match. Like so. And we would graph it out. Okay, so there you go. That's how that's using the steps, right? The last thing we do, okay, is we would add the 2. And the 2, what this does, right, is this doubles. So you would multiply the y values by 2. So we can go ahead and we can do that, okay? The root is already done. So we're just going to take our graph that's in blue and we're just going to multiply all the y values by 2. And that's what our actual new graph will look like. So instead of it being at y equals 1, it's now y equals 2. This will be at 4, okay? And this will be at 6. So this is 4, 5, 6. Still starts at y equals 0, and it creates the graph. There you go. Okay, so I showed you this because you can do it in multiple ways. You can use mapping notation, or you can use the characteristics of radical functions to graph this. Okay, depending on your teacher, you may be asked to do both. Okay, so I'm just wanted to show you both just to make sure you have both. Okay, next example we have is determine the roots of the root of x plus 5 minus 3 is equal to 0. So again, this is just finding what x equals, right? You're trying to find where this graph crosses the x-axis. That's all you're trying to find. Okay, so we have the root of x plus 5 minus 3. So what we'll do is we'll add 3 to both sides. Okay, we get the root of x plus 5 is equal to 3. Next, what we'll do is we will square both sides. So now we get x plus 5 is equal to 9 minus 5 from both sides, right? So you would take away 5 from both sides, which means you get x is equal to 4. Okay, if you were to check to make sure that this is right, you say let x equal 4. Okay, so then we have the root of 4 plus 5 minus 3 is equal to 0. Well, 4 plus 5 gives you 9, right? Okay, the root of 9 is 3, and 3 minus 3 is 0. So we can safely say that this works. Okay, so this means that we cross the x-axis at this. We cross the x-axis at 4. Next example, okay. Part B. Find the x-intercepts by graphing. So what we'll do is we'll graph this. Y is equal to the root of x plus 5 minus 3. So again, what we can do is we can say, well, what's happened to this graph, right? So for our regular, y equals the root of x, right? We have 0, 0, 1 and 1, 4 and 2, 9 and 3. So remember, everything under the root, okay, you'll do the opposite of, and that's going to affect your x values. Okay, so it says x plus 5 under the root, when really we're going to take away 5 from our x values. Everything outside the root, okay, affects your y values. So it says minus 3, so we're going to take away 3. Everything outside the root, you do exactly what it tells you. Okay, so instead of it being at 0, 0, it's now at negative 5, negative 3. Instead of it being at 1 and 1, okay, it's at negative 4 and negative 2. Okay, next you have is at negative 1 and negative 1. 9 and 3. Okay, so that's going to be at 4 and 0. Okay, so let's go ahead and let's plot these out and let's graph it. Okay, so we've plotted our points. All right, let's graph it out. All right, so we've now graphed it out. We can now pinpoint where the x-intercept is. So So the x-intercept is at 4. There you go. Okay, last example. It says solve the equation. The root of x plus 5 is equal to x plus 3, and we need to solve it graphically. Okay, so what that means is we need to find the intersection between the two. So we're going to draw two graphs. So I'm going to say y1 is equal to the root of x plus 5. Okay, and then I'm going to say the next one, y2, is equal to x plus 3. And what we need to do is find the intersection. Okay, find out where they meet, find where they cross. Okay, that will be our answer. So I think we can safely graph the x plus 3 with no issues. So I want you to go ahead and do that. Okay, so this is what x plus 3 looks like. And now we can graph the x plus 5. So again, everything's the same, except we've shifted this graph to the left by 5, okay? Because that's because it's under the root. Okay, so everything's the same, but you're going to move it to the left 5. So 1, 2, 3, 4, 5. Okay, so that's going to be where our starting point is. Then you're going to go up 1. Okay. Then the next point would be at 4 and 2, but you're going to move it over to the right by 5. So we get -5 and 2. Or sorry, -1 and 2. My mistake. Okay, and then the next point would be at 9 and 3, but you were shifted over to 5. So that's going to be 4 and 3. So 1, 2, 3, 4, and 3. So we can go ahead and we can graph this out. So it looks like this. Okay. Where they intersect is right here. So that is your answer. So the solution to this particular problem is that x is equal to -1. So that is your solution, okay? Just a quick little thing before, just a quick little note. The only answer is x isn't equal to -1. Now you're probably wondering, well, why don't we include y? In the original question, there are no y values, right? It's only x values. So that's why in our answer, we can only state the x value. There are no y values. So let's just make sure we write that down. Okay, so the solution is the x value only, as there are no y values in the equation. Well, that is it for today's lesson on graphing radical functions. I hope you enjoyed it. Again, when it comes to math, keep calm and show your work.